Hi, my name is Lorian Pratt, and in this video I will review a decision model that's designed to help cable operators as they make some pretty complex decisions, specifically surrounding generating their own energy. Now, in previous videos, we've looked at models that talk about the value of renewables that cable operators might purchase, and looked at some of the complex factors there. This one is a little bit more specific. It's around energy generation. So, for instance, you're a head end and you might want to put some solar panels on the roof or build a wind farm nearby. What are the factors that are going to weigh in to whether you can ultimately achieve a return on that investment, and when can you expect to enjoy that return on that investment? So we'll build this up piece by piece. As a whole, the model's complex, but each piece is pretty simple, and I hope by the end of it you have some great insights into how to go about making these sorts of decisions. This model starts out with just a calculator of the subscribers per head end. We have a simulation where we run a 200-week simulation starting out with a particular set of homes passed, a particular penetration, and then those two numbers grow through a 4-year expected subscriber growth percentage. And so just to get really clear about that, we figure subscribers can grow 25% over a 4-year period at a particular head end. Now you may have other CAGRs that you want to put in here, and this model allows this to be substituted pretty straightforwardly. So just really quickly, this first part of the model just shows subscriber growth. And we can run a little simulation that shows this green line here, where basically subscribership grows roughly exponentially over the course of this simulation. So that's just the first part of the model. Next, we'll start looking at how much power each one of those subscribers uses. And what we're going to get to here is the kilowatt hours per subscriber, again, at a particular head end in a given week. And we're going to use that number going forward to say, okay, given that we have a certain number of subscribers and a certain amount of energy usage per subscriber, what's the cost of that going to be? And then how can we offset that cost by doing some renewable generation? So to get the kilowatt hours per subscriber, we just take the watts per subscriber, and we'll talk about how we calculate this in a minute, and then just say, well, if we're going to be supporting those subscribers every hour, 24/7, how do those watts translate into kilowatt hours? Now, watts are kind of interesting here because they're measured using two factors that kind of counteract each other. Number one is, according to our projections, subscribers are going to get increasingly thirsty for CPU power, for more video channels, for more sophisticated equipment to support broadband and video on demand and other services. So the CPU load, the compute power per subscriber, those requirements we anticipate are going to go up over time. At the same time, the watts per CPU load unit is going to decrease. The inverse way to say this is the performance per watt is increasing. Basically, equipment is getting greener, and so we can get more and more compute power for fewer and fewer watts out of equipment as we move forward into the future. So these 4 boxes here just are going to capture those kind of countervailing factors that work against each other. And what they do is they're multipliers on kind of some basic rates that we have here. In particular, each subscriber's service is going to impact equipment at the head end, but also at the node and at the hub. And let's go straight into the exact numbers here. Our estimate is, again, on average in the U.S., and you'll want to put in your own individual numbers here, but our numbers are a good starting point that show about 2 watts per subscriber for head-end equipment, about 2/3 of a watt at a node, and then 13 watts at a hub, for a total of 16 watts per subscriber at the first week of our simulation. And then again, these 4 boxes are going to apply a factor to that, and we'll just run this manually for a second so you can see what it does. So what happens is I'm increasing the weeks here, and you can see that the CPU load, as a function of the first week load, we're just saying the first week load, we'll call that 1, and then the CPU load per subscriber in later weeks. Here we are at week 76, at about 1.5 years into the simulation, and each subscriber is using about 1.5 times as much CPU power as it did at the beginning of the simulation. Now, at the same time, each unit of CPU power is costing about half as much in terms of wattage. And so again, these two factors kind of work against each other, but essentially the benefits outweigh the costs. And so these total watts per subscriber that we experienced in the first week of the simulation, which was at 16, is down to 13. And I'll just tell the simulation to stop after 200 weeks. Week greater than 200, and reset the model, and we can watch the full simulation run. And what you'll see is you'll see weeks increasing slowly, and then you'll see the wattage gradually decreasing on a per subscriber basis. So good to know that we are actually going to be decreasing the amount of power per subscriber. But if your subscriber projections are as rapid as ours are, then actually you're going to end up using more energy per head end, and let's get into that next. So here's where we start to put this all together. We calculate the total required kilowatt hour per head end in a given week, and that's going to be a function. I'll just show you this formula here. That'll be a function of the kilowatt hours per subscriber in a week. So this is how much energy each subscriber uses, and then how many subscribers there are anticipated to be supported by each head end. So it's just multiplying those two numbers together to get the total kilowatt hours required at a head end. And then the question is, how much is that energy going to cost? And we found some EPA estimates that show some forward projections of these numbers, and we drew those in a graph to emulate what we had seen in this other projection, which basically what you can see, this runs out 3 scenarios, and for the next 2 or 3 years, the 200 weeks of our simulation, these scenarios are essentially the same, and that's what we captured in our graphs. And so let's do kind of the first bottom line is if we were buying all energy, all of those kilowatt hours for a head end from the grid, how much would that cost in total as we go forward? And you can see that this is showing that the first week it would cost approximately $45,000. But all of those other factors we talked about are ultimately going to change that number. And the question is that going to go up or down? So let's take a look and see what happens here. Generally speaking, what you're going to see is an exponential growth as we go forward to about the 200-week mark. This is the cost value that essentially we're trying to remove. We want to try to take that out of the system and substitute solar or some other renewable energy. Again, in our example, we're using solar, but this same model structure could be used for a number of different technologies. Obviously, some of these assumptions would need to change in a few places, but those should be pretty clear as you take a look at it. So here's the decisions that MSOs face. How much does it make sense financially to invest in a transformation to a renewable generation capability, such as, again, solar panels on a head end is the example that we're using here. And so the decision lever is represented by this curve here. This is just representing the amount of investment that an operator might want to place in a solar transformation over the 200-week period. Now you can see this is kind of backloaded, and the reason I chose to do that was because solar gets cheaper later on. As we move forward in time, we're going to see decreasing costs for solar power. In fact, I'll backload this even further. We'll say we'll just do a little bit of investment at the beginning, just do some trial and proofs of concept, and what happens if we backload this. So this is the decision lever that you face. This is where you have some latitude to make some choices. And this choice is going to marry together with data in the future as it plays out. In particular, as I said a moment ago, the price per watt of solar is expected to decrease. And that sort of means that if you delay this program a little bit, well, then that could provide a benefit. On the other hand, the longer you delay the time to reduce your operational expenditures that you pay for increasingly expensive grid power. So we've got all these crazy factors that are interacting with each other. And this model is meant to help you to understand a little bit better and to get aligned with your team as to how those factors do interact. So what I've captured here is a number called the total solar investment so far. And that's just going to be, I'm going to add up, each week how much we pay for solar, just so we can track that. The next factor here is the number of watts that's purchased in a given week. So this just takes the price per watt of solar as we project it going forward, marries that together with how much we're spending each week, and that will tell us how much we can buy in solar generation capability. So this is not kilowatt hours that we're buying. We're not buying power off the grid. We're buying generation capability. So when I say watts here, we're not really buying power. It's just solar panels that can generate that power. Now, given that we have a certain amount of solar panels in a given week, we can end up generating a certain number of kilowatts. When we combine that with the number of hours in a week, we get the kilowatt hours that are provided by solar in a given week. So this whole kind of upper left part of this graph is all about building out some kind of a renewable capability and how much that costs, and then what you end up getting for that, which is a certain amount of power that's generated by that facility, which offsets what you might otherwise have to pay for on the grid. Obviously, once you've bought the solar panels, you don't have to pay further for ongoing power. It comes out of the sun for free. So if we take that total kilowatt hours that the solar farm is now able to generate, and we divide that by the total kilowatt hours that all subscribers need at this head end, we get this percentage shift to solar. So what we'll see in the simulation in a moment is that this percentage shift is going to increase gradually over time, and that's really based on all of these other factors on the left-hand side of the graph, which involve, how much are you spending on solar, and then how much does a watt cost, and how does that all add up to a capability of generating your own power. So really, the bottom line of this model is in these last few boxes in the lower right of this graph. And I'll draw your attention to these two to start with. If we were not to build a renewable generation capability, then we'd be buying our power off the grid, and that would have a particular cost. And that cost on a weekly basis is captured here. And then I accumulate that cost so we can see kind of what the total cost over this 200-week simulation period would be if we did not purchase renewables. On the other hand, if we do purchase renewables, then we're going to still pay for grid power, but maybe not as much, right? If we've converted 30% of our kilowatt hours that we need every week, then we only need to buy 90%, sorry, 70% of the power that we otherwise would have had to buy. So that grid energy cost will be lower. But of course, we've got to account for the fact that we also spent some money to get there, right? We had to do this per week investment in solar transformation. So that's what's captured in this cumulative grid energy cost. This is meant to be all of the costs, both the grid power that you have to buy, as well as the cost of the solar panels when you have a renewables program. And what we're doing is we're comparing that to the cumulative cost if we did not have that renewables program. And so what I'm going to do in this simulation is I'll set things up such that we can track those two cumulative costs, and then we'll also watch them change on the right-hand side. So let me set this up for you. And we'll take off the thing that we had before. And then the other thing that I like to do here is, again, to track this total solar investment, just so we can see how that's a component of it as well. Okay, so we'll start this simulation, and I'm going to tell it to stop after week 200, because that's where I really had those curves. They only go out to 200 weeks. What you're going to see here is the cost of the total solar investment so far. So that's the green line. That's how much we've paid. And the red line is the cumulative grid energy cost given that we've made a solar investment. So that's going to actually be the sum of the green line plus the grid energy cost. And then the turquoise line is if we didn't have a renewables program at all. So we can see at first that, that solar program's costing money because the red line is above the turquoise line. But look what happens after a little while, and certainly this trend would continue if I ran it out past the 200 weeks. We start to really diverge, and it's kind of what you expect is after you've made an investment in a transformation program and you've kind of gone into the red here, where the red line is higher than the turquoise line. We've really made an investment. We've lost money in the short term, but the long-term benefits are really quite considerable. So the last thing I'll do in this model, just because I think it's kind of interesting, is to change this per week investment pattern and to say, how does that behavior shift if instead of having kind of this back-ended investment like I have here, I do another shape. Let's start our solar program much earlier and maybe terminate it. Only invest a little bit in solar panels, and maybe we'll end up purchasing less of them than we would have otherwise purchased. So there's the shape now, and then I'll reset this simulation, and we can see if that makes much of a difference to the simulation. Again, that's the green curve that would pretty much exactly emulate. Actually, the green curve is a cumulative of that one. And we do see a little bit different shape. We're still in the red for a while, right? Where the cumulative grid energy cost given the solar investment is higher. But once again, we really do start to diverge. And in this case, we're actually diverging further. So I hope this is helpful. This is a model that if you contact us, we can make it available and also support you in getting the best data you possibly can for your particular situation into it. Certainly the price of solar is different in different regions. The price of grid energy is different depending on where you're located. Different operators have different expected subscriber growth patterns, and all of these factors are going to impact these ROI curves. This model is a good starting point to understand kind of how all of these complex factors interact, and to help to share with your team that there really can be a substantial benefit under many different scenarios of shifting to generating your own power. Thank you very much. Please contact us at Quantellia if you have any further questions. Thanks.